All right. Welcome. Seems like a few people are missing, but let's get started anyway. Maybe they'll join us online. Just a reminder, if you haven't collected your exam yet, I have them with me. So if after class you need to pick up your exam, that is great. Any homework questions over implicit differentiation? Yeah.
63.
63.
Specifically part B, but I think you have to do most of it.
Okay. So 63. We have y times x squared plus 4 equals 8. Okay, and they said first use implicit differentiation to find dy dx. Okay, we can do that, and then we'll get to part B. So if I just take the derivative of this thing implicitly, then I have a product rule on this side, so I get the first, which is y, times the derivative of the second, which is 2x, plus the second, which is x squared plus 4, times the derivative of the first, which is the derivative of y, or dy dx, is equal to, on the other side, the derivative of 8 is just 0. Now I just need to solve for the dy dx. So I can move this thing to the other side, and I get x squared plus 4 times dy over dx is equal to negative, I suppose I could just write this as negative 2xy. And then I can divide both sides by x squared plus 4 to give me that dy over dx is equal to negative 2xy divided by x squared plus 4. So far, so good? Okay, so then part B is the question, find equations of all tangent lines to this curve when y is equal to 1. Okay, yeah. So if y is 1, so this is part B, where y equals 1. Well, if y is 1, let's go back to the original equation and see how many x values show up. Okay, because this is not necessarily a nice function, it's a curve, right? So if y is 1, how many x's do I get? So I get 1 times x squared plus 4 is equal to 8. In fact, this is actually a function because I could solve it for y, but I can figure out either way what is the x values. So x squared is equal to 4, and x would be plus or minus 2. Okay, and they're saying, could you please figure out what all the lines tangent to the curve, find the equations for them when y is 1. Okay, so if y is 1, then I get x is plus or minus 2. So there's 2 points that are interesting to me. 2, 1, and negative 2, 1. So I want to find a tangent line for both of those points. To find a tangent line, I need a point and I need a slope. So this is the way that I find the slope, is I plug one of these points into this equation to find the slope at that point. So I could say, what's dy dx evaluated at the point 2, 1? And this little bar, when you draw that little bar after something, it just means evaluated at. So I'm going to plug something in. And I'm going to plug in x is 2 and y is 1. So if I do, I get negative 2 times x, which is 2, times y, which is 1, divided by x squared, so that's 2 squared plus 4. So that gives me a slope of, on top I've got a 4, on bottom I've got 4 plus 4 or 8. So this is negative 1/2. Okay, so now I have a point and its corresponding slope. So at the point 2, 1, I have the following tangent line. I get y minus y1, which is 1, is equal to m, which is negative 1/2, times x minus x1, which is 2. And now I could solve that thing for y and get y minus 1 is negative 1/2 x plus 1. Add 1 to both sides, and I get that y equals negative 1/2 x plus 2. So that's one of them, correct? Now I've got to do the same thing with the point negative 2, 1. So I'd say let's let dy dx, let's evaluate that thing at minus 2, 1. If I do, I get negative 2 times x, which is minus 2, times y, which is 1, divided by x squared, which is 2 squared, plus 4. Oops. Plus 4. Okay, so that is equal to negative times a negative is positive. So on top I've just got 4, and on bottom I have 4 plus 4, which is 8. So I just get positive 1/2. Now do the same thing, complete. What is the equation of the tangent line? So at the point negative 2, 1, I get y minus 1 equals 1/2 x minus negative 2. So I get y minus 1 equals 1/2 x. This is plus 2 times 1/2 is plus 1. Yeah, and then I just add 1 to both sides. I get y equals 1/2 x plus 2. And that's it. Sound good? Do I need to keep going, or that answers your question? Okay, perfect. Other questions? Yes?
Number 47.
47, okay. So 47, we're wanting to verify that the given points lie on the curve. Okay. And then determine an equation of the line tangent to the curve at the given point. Okay, 47. So 47, we have x squared plus xy plus y squared is equal to 7 at the point 2, 1. So the first thing they want us to do is just say, does that point fall on the curve? And then find the equation of the tangent. Okay, to find out if the point lies on the curve, you just plug it in and see if it actually is equal to 7. So if I plug in 2 for x and 1 for y, do I in fact get 7? So I just plug things in. I get 2 squared plus 2 times 1 plus 1 squared. And what is that? So 4, 5, 6, 7 is 7. So that works out. Okay, so now we want to know what's the equation of the tangent line at that point. But to do that, I need dy dx, right? I need the derivative. I have the point, so that's nice. I just need to know what's the slope at that point. So I'll use implicit differentiation to find the derivative of this function. So the derivative of x squared is 2x. The derivative of xy is a product. So I need to use the product rule to find the derivative of x times y. So it's the first x times the derivative of y, which is dy dx, plus the second y times the derivative of x, which is just 1. The derivative of y squared is 2y dy dx, and the derivative of 7 is 0. So now I have some stuff that has some dy dx's in it, and I have some stuff that does not. So let's leave all the dy dx stuff on the left side, move all the non-dy dx stuff to the other side. So if I do, I get x dy dx plus 2y dy dx is equal to, I move these guys over, this one comes over as a negative 2x. I move this one over, it comes over as a minus y. Now I can factor out on the left side the dy dx, and I get dy over dx times x plus 2y is equal to negative 2x minus y. Okay? Now, we can divide both sides by x plus 2y, and I get that dy over dx is equal to negative 2x minus y divided by this stuff, which is x plus 2y. Okay, so now I have an equation for the derivative. Now I just need to say, well, what point do I care about? The point that I care about is at 2, 1. So I'm going to say, what's dy dx evaluated at the point 2, 1? So x's are 2's, y's are 1's, and I get negative 2 times x, which is 2, minus y, which is 1, over x, which is 1, plus 2 times y. Oh, what am I doing? Ooh, did I mess that up completely? No, the top was fine. This I just messed up. So x is 2, y is 1. Yeah, that seems okay. All right, so what does this end up being? We have 2 times 2, negative, minus 4, minus 1 more. It's minus 5 on top. On the bottom, I get 2 plus 2. That's just 4. So negative 5/4. That's my slope. Okay, so I have a point, 2, 1. I have a slope, negative 5/4. Now I just need to use point slope equation of a line to find the equation of that line. So I say y minus y1, in this case that's 1, equals m, which is minus 5/4, times x minus x0, which is 2. Now I could solve for y. I get y minus 1 is equal to negative 5/4 x plus, if I multiply that by 2, that's 10/4 or 5/2. So plus 5/2. And now I could just add 1 to both sides of the equation. I get y equals negative 5/4 x. And then 1 is the same as 1 is the same as 2 halves. So 5 halves plus an additional 2 halves would be 7 halves. And that would be the equation of the tangent line. Now, if you're ever sort of in doubt about your answer, you should kind of ask this question. Is this point on the tangent line? Because if it's not, you did something wrong. So that's a good, it doesn't completely answer your question for you if you did it right or not, but it helps. So plug in the 0.21 over here and see, does it work in the equation? So if I plug in that x is 2, so if x were 2, this would be -5/2 plus 7/2, which is 2/2 or 1. So if I plug in 2, I get out 1. At least that's a start, right? It means that it does go through the right point. Did it have the right slope? Well, we don't, I mean, we assume so. But if that's off and you can't even plug in the point to your tangent line, you know you're wrong. Okay. Other questions? Yes.
39.
39. Okay. So we're just finding dy dx. So 39 is square root of x to the 4th plus y squared is equal to 5x plus 2y cubed. And we're just finding dy dx. Okay, so let's just take the derivative of each side how it is right now. The derivative of this guy, I have something to the 1/2 power, right? So I start, this is a chain rule. I have something raised to the 1/2. So the derivative of something to the 1/2 is 1/2 times whatever's inside, in this case, x to the 4th plus y squared to the -1/2 times the derivative of what's inside. In this case, what's inside is this x to the 4th plus y squared. The derivative of x to the 4th is 4x cubed. And the derivative of y squared is 2y times dy over dx. Okay, so that's the derivative of the left side. The derivative of the right side is going to be equal to, well, the derivative of 5x is 5. The derivative of 2y cubed is 6y squared times dy over dx. Okay, whenever you have a problem like this, it's really important that you do something. And that is this dy dx, it's kind of not by itself. It's kind of tied in with this 4x cubed and then multiplied by something. So the first thing that I like to do on a problem like this is take everything that's multiplied here and distribute it to these two things. And the reason why is then you get a dy dx that's just multiplied to something. It's not added then multiplied. It's the same as if you were solving for x. You want to get x sort of by itself. And the way you do that is you don't want it to be added and then multiplied to something else. So let's distribute this whole thing to both of these guys. If I do, I get, let's see, 4x cubed times this guy. So this is 4 times 1/2 is 2. So I have 2x cubed times x to the 4th plus y squared to the -1/2. Okay, so I multiplied this whole thing times this guy. Then I want to multiply this whole thing times this one, which will give me plus 2 times 1/2, those cancel. And I have a y. I have this x to the 4th plus y squared to the -1/2. And then I also have the dy dx times dy over dx. Okay, so this, I took this whole thing, multiplied it here, took this whole thing, multiplied it here, and now I have this. And now on the other side, I still have just 5 plus 6y squared dy dx. Now is when you would say, okay, can I get all the dy dx stuff together? There's a dy dx thing here. There's another thing that has a dy dx here. Let's put all the dy dx stuff on the left and all the non-dy dx stuff on the right. So this guy gets to stay. So I have y times x to the fourth plus y squared to the negative 1/2 times dy dx minus 6y squared times dy dx is equal to, on the other side, I'm going to have this 5 that's just still hanging out. And then all of this term, I'm going to move to the other side as a minus 2x cubed times x to the fourth plus y squared to the negative 1/2. Okay, so what I've done is I've got all the dy dx's on the left, all the non-dy dx's on the right. The reason I want to do that is now I can factor a dy dx out of the left side. Okay, so let me do that. So I have dy dx times, and what's left over is I have y times x to the fourth plus y squared to the negative 1/2 minus 6y squared equals, and the other side stays the same. Okay, so now I'm actually ready to write my final answer. Now I just need to divide both sides by all of this stuff to get the dy dx by itself. So let me write that real quick. So we'll say that dy over dx is equal to this stuff, which is 5 minus 2x cubed times x to the fourth plus y squared to the negative 1/2 divided by all of this stuff, which is y times x to the fourth plus y squared to the negative 1/2 minus 6y squared. And that's not like the prettiest thing I've ever seen in my life, but it is the derivative. Somebody might ask the question like, well, could you clean this up at all and make it look a little bit better? Maybe. It would look better, but not best. I think that you could multiply the top and bottom by x to the fourth plus y squared to the 1/2. And it would get rid of these, but then it would just add it to the other ones as a positive 1/2, which does look better. There's no negative exponents running around, but it's not really much less complex. So this is about as good as it gets. Okay. And we shouldn't be like shocked that this has a complicated derivative when we look at the original equation. It's like, that's not a very nice curve. And so we shouldn't be surprised that its derivative is a little bit complicated. Who asked that one? That answer your question? Okay. Yeah, some of these implicit differentiation problems, they test your algebra skills, right? It's kind of like, hey, do you remember your algebra stuff? And then the bigger question is like, it's really important that you get the derivative right. It's kind of like there's two pieces to these problems. It's first of all, do you get the right derivative? Just step one. And then from the derivative to the end, it's kind of like, can you do some kind of like, it's not super hard, but it's harder than we've been doing algebra. So those are kind of the two big pieces of these implicit differentiation problems is, can you get the right derivative, and then can you simplify it? Other questions?
On the step where you're multiplying out,
Yes.
I'm a bit confused on that.
Yeah, here. Yep. So let me put it in terms of something else, and it might be helpful. Okay. Let's say that I have z times x plus y is equal to 4. And I say, let's see. I don't like, yeah, okay. Let's say 3 plus z. Oh, yeah. Okay, let's take something like this. And I say, solve for y. Okay, so let's get the dy dx's. Sometimes I think that having dy dx's just like intimidates our algebra skills a little bit, but nothing's really different. Dy dx is just a thing, right? And we're solving for something. And like, let's say it was y in this case. Well, if you wanted to solve for y here, it's not so great to like divide both sides by 3 plus z. Because now you almost have the same problem, because now there's a y kind of like caught up in here. The best thing you could ever do is like, we need to like get this y is just all by himself, which is great. This y is not by himself, that's not great. So probably what you would do is you would say, well, let's multiply this out and write this as 3 plus z times x plus 3 plus z times y is equal to 4 plus y. Now the y is sort of like by itself, right? So now you can isolate the y's and factor a y out and then solve for y. That's what I'm doing over here, is I'm saying, what's my variable to be solved for? Dy dx. So I sort of have to isolate the dy dx. And how do I get just dy dx stuff on one side of the equation? Well, right now, there's some dy dx stuff here times this stuff, and then there's some non-dy dx stuff times this stuff. That's non-isolated, right? And so what I need to do is I need to find a way to get that other stuff away from the dy dx. And the only way to really do that is to distribute through by this stuff. Just think of this as a big X, right? So I just have X times these two things. Then I multiply X times this, and now I can move this to the other side and get the non-dy dx stuff out of there. It looks nasty, but it's really stuff that you've done before. But I do understand that when you first start doing implicit differentiation problems, like if you just look at the board, you're kind of like, yikes, there's a lot going on. But it really is the same algebra that you've always done. You just have to say, what's my variable and how do I get it by itself? I think the temptation that some people have that's wrong is, and this is where people mess up all the time on implicit differentiation, is they take this thing and instead of multiplying it through, they divide both sides by that. Because they're like, I need to get rid of this. So they divide it to this side, but that's no good because now this is stuck. So it didn't actually make life any better to divide both sides by this thing. The best thing to do is distribute it, and then you're good to go.
So you just take the entire expression, multiply by 1.
That's right. Entire thing multiplied by this guy, entire thing multiplied by this guy. Does that make sense? Yeah, just treat this as if it were a humongous X, And it's just like x times this plus x times this. Yeah. Other questions? Yes,
23.
23. Let's look. So 23, I just want to find dy dx, okay. And then I want to find the slope of the curve at a point. Okay. So number 23, we have the cube root of x plus the cube root of y to the fourth is equal to 2. And then the point we want to use is 1, 1. Okay. So first of all, if I would like, I could change these into exponents instead of having like cube roots everywhere. I think it's better. So I could write this as x to the 1/3 power plus a y to the 4/3 power is equal to 2. And I think that's going to make it easier. And so now if I take the derivative of x to the 1/3 is 1/3 x to the what?
To negative 2/3.
Yeah, negative 2/3. And then the derivative of y to the 4/3 would be 4/3 y to the 1/3 times the derivative of y, dy dx. And then on the other side, I just have 0. Now I just need to solve for dy dx, so let's get non-dy dx stuff to the other side. And I get 4/3 y to the 1/3 dy dx is equal to negative 1/3 x to the minus 2/3. And then I divide both sides by 4/3 y to the 1/3, and I get that dy over dx is equal to negative 1/3 x to the negative 2/3 divided by 4/3 y to the 1/3. Okay, that is certainly true. That is kind of ugly right now. I think I could do better. Let's see if I could simplify that a little bit. I could certainly multiply top and bottom by 3 because there's a 1/3 on the top and 1/3 on the bottom. Those 1/3 would cancel. And I could write this as negative x to the negative 2/3 divided by 4y to the 1/3, which is fine. And you could leave it that way if you wanted to. The x has a negative exponent, so you could put that on the bottom if you wanted to. I don't know that it matters a lot if you do that or not, but you could if you don't like negative exponents. So you could write the dy dx is equal to negative 1 over x. Oh, I guess I have 4x to the 2/3 times y to the 1/3. So that would be one way to write it. And then the question is, well, what's the slope at this point, 1, 1? So what's dy over dx evaluated at 1, 1? So I'll just plug in 1 for x and 1 for y. So I get 4 times 1 to the 2/3 times 1 to the 1/3. And I get 1/4.
What do you mean negative 1/4?
Oh, thank you. Lost a negative.
Is there anything that stops you from just raising the whole equation to the 3rd power at the very beginning? Just get rid of those? Because I got a different answer.
Yeah, it's not. I'm not saying you can't, but maybe you shouldn't. And let me show you why. I'm thinking that what you're thinking of raising to the third power and what I am are different.
Probably.
Okay, so what you can certainly do is you could take this and say this is cube root x plus cube root of y to the fourth cubed is 2 cubed.
Yeah.
That's true. This, though, is not really that nice. You don't get to distribute the cube. It's this thing like written 3 times, foiled out. So it's actually like a lot worse, right? If you just want to say, well, this one cubed plus this one cubed equals this one cubed, that's not true, right? A great example of that is like if you, let's say that this one's 1, and this one's 1, and this one's 2. So is this one cubed plus this one cubed equal to this one cubed? No. So we got 1 cubed is 1 plus 1 cubed is 1 plus 2 cubed is 8, and 1 plus 1 does not equal 8. So we can't just cube across an addition. You have to cube the entire sum. Yeah. That's a good rule of thumb in general, is if you like come up with like, I don't want to call it a magical formula, but like it's kind of like if you come up with a formula in your head and it's like, what if I could just cube both sides? Like, and you cube over the addition and you're not sure, it's like, just take some numbers and say, does it work for those numbers? And oftentimes, I mean, I've done this many times, even on exams, I'm like, wouldn't it be great if this were true? And then I said, okay, what if it's 1 and 1 and 2? And it's like, it's not true. So I guess I better not do it. So yeah, let me see. Some people have written online. Okay, quite a few, just like 20, 35. Have we done 35?
I don't believe so.
No, we didn't do 35. And a couple different people mentioned it online. So maybe let's do 35. Okay, so 35, we just want to find dy dx. So I have x cubed is equal to x plus y divided by x minus y. Okay, and we want to find dy dx. So let's just take the derivative of this saying implicitly. The derivative of 3x is 3x, x cubed is 3x squared. And then on the other side, the derivative of this thing, that's a quotient, right? So we need to use the quotient rule. So we get the bottom, x minus y, times the derivative of the top. The derivative of x plus y is 1 plus dy dx. Minus the top, which is x plus y, times the derivative of the bottom, which is 1 minus dy dx, all over the bottom, which is x minus y squared. Okay, so this is like a really fun one where it comes to like, how do we isolate the dy dx? So the best thing to do, I think, is here we need to multiply through by the x minus y. Here we need to multiply through by the x plus y, so we can kind of get the dy dx's together. Here I do want to multiply both sides by x minus y quantity squared to get this out of there, so that I can isolate those dy dx's. So I'm going to rewrite as 3x squared times x minus y squared, right, is going to be equal to, if I multiply through by the x minus y, I get x minus y plus, that's times 1, plus x minus y times dy dx. Then I get minus x plus y times 1, so minus x plus y. Then I get minus x plus y minus times minus dy dx, which is, so I've got a minus times a minus is a plus x plus y dy dx. Okay. Now, something interesting happens here. I've got an x and I've got a minus x. So the x and the minus x cancel. And I've got a minus y and a minus y. So that's minus 2y. So on this side, I have minus 2y that I need to move over to this side. So it's going to come over as a plus 2y. So I have 3x squared, x minus y squared, plus 2y. So that got rid of this minus y and this minus y. And that's equal to, on the other side I have, let's see, does anything cancel? It does if I wanted it to. So I maybe can make my life a little bit easier because here I have an x dy dx. I have a minus y dy dx. I have a plus x dy dx. And I have a y dy dx. And the y and the negative y dy dx cancel. And so I'm just left on this side with 2x dy dx. Okay, so let me rewrite this one more time. I have 3x squared times x minus y, quantity squared, plus 2y is equal to 2x dy dx. And now the only thing I have left to do is divide both sides by 2x. So I get that 3x squared times x minus y squared. I'm sorry, x minus y, quantity squared, plus 2y, divided by now 2x is equal to dy over dx. And that's it. Okay, what time is it? We've got 6 more minutes. I think that that's a pretty good place to stop. I think it's giving you the general idea of what you need to do and where do the problem spots come up. And I think that the problem spots where people mess themselves up is when they have to get down to solve for dy dx. And typically the reason that they mess up is because they fail to distribute. They try to do some other cute trick. And don't be cute. There's no way out of like some nasty algebra on these problems. You just have to multiply it out, get the dy dx's together, get everything else on the other side, and then divide. So it's kind of the same every time, but I agree the algebra can be a little bit nasty. Okay. All right, that's it for today. You can go ahead and get started on the next homework assignment. This one's due today. The next one will be due on Monday. So have a great weekend. I'll see you there.